So kind of interesting to think about. All right, so let's move on to neural networks and deep learning. So we're going to take you way back to like early 2010s, right? About what we were thinking about AI. So the first is that there is a bit of terminology soup that you need to kind of know and get used to, right? Because I'm going to use these terms and kind of expect you to know it, right? So the first is AI, which is an umbrella term for intelligence from a machine. Okay, so just AI is just anything that's kind of intelligent from a machine, okay? Now, I've seen some arguments about this terminology in particular. Some people think that intelligence is being able to solve a problem in more ways than one. Okay, so just think about that, more ways than one, okay? Because if, for example, you write like some software code, it's just going to solve the problem in the exact same way every single time, right? Because it's very programmatic. So we do not consider that to be intelligence, but it's more like it will try and solve a problem, solves a problem, it runs into like a barrier, and then it adapts to get around that barrier, okay? So that's kind of like what intelligence is. And so, intelligence is actually not that complex, right? Because a lot of animals have intelligence. If you put like a wall in front of a rat or something, right, it's going to be able to run around that wall. So that is already intelligence, right? And so yeah, AI is something that's kind of able to do that. And so yeah, just kind of an umbrella term there. AGI is something that you might hear, which is generalized AI across different domains. A lot of people kind of argue about that. I actually think that we've already reached AGI, right? Because ChatGPT is able to do intelligence or exhibit intelligence across a lot of different domains, right? It's not just, can just solve math or can just solve English or whatever it is. It can solve lots of different things. ASI, which is super intelligent AI, again, lots of discussion, but one thing that a lot of people have kind of agreed on is that it's better than 99% of humans at a wide variety of tasks. Okay, so I don't think we're there at all yet, right? So, but the kind of goal of a lot of these AI labs is to reach super intelligent AI. So that is AI that is intelligent and much better than humans. And big question is, are they just trying to replace humans, right, at a lot of these tasks? But that's kind of a goal at some of these labs. Now, some older terms that you might see, so machine learning. This is a subset of AI that focuses on statistical learning. So it uses mainly statistics to learn something. Deep learning is a subset of machine learning that uses neural networks in particular. Okay, so we still technically do deep learning, but no one really calls it that anymore because you'll see that transformers are technically kind of neural networks with some extra stuff, right? But you don't really see this term as much anymore. And then generative AI is a subset of machine learning that uses transformers. Okay, so hopefully you've heard of that term before. Okay, so let's talk about neural networks. So neural networks are a very kind of basic mathematical tool, actually. And it comes from this really simple thing named linear regression. Now, does anyone know about linear regression? Can I just kind of get a show of hands? Yeah, maybe? Okay, so linear regression, very basic. Essentially, you have a list of inputs, and then you need to predict a specific output. Okay, very simple. So say, for example, our task is to predict the length of stay of a patient at a hospital. What kind of stuff would you input into that? Ideas? Sorry? Yeah, their condition, their age. What else? Perfect. That's it? What else would you input? So think kind of more broadly here. Diagnosis? Absolutely. You want to know what disease they have, right? What else? So what was that? Urgency. Yes. How urgent it is, how emergent it might be. What else? Ideas from this table here? Yeah, space in the hospital, right? So it could be that, if the hospital's running out of space, you've got to kick people out, right? So the length of stay might decrease, right? What else? Yeah, exactly. Everything, right? As much as you can, right? And so, yeah, so say you have linear regression, there's just a lot of stuff, right? I've just listed a bunch of stuff, obviously, et cetera, right? But you might have age, diagnosis, comorbidities, how they presented, did they go in an emergency, an ambulance or not, right? What kind of medications they might have, what procedures they might have received while they were in hospital. What their living situation is. If they're elderly, maybe you can't discharge them back, right? Because they can't look after themselves, right? How frequent their past admissions are. And the output you're trying to predict in this stage is the length of stay in the hospital. And so linear regression basically means that you're trying to predict this, so this specific output, based on this entire list of inputs in a linear way. So you basically assign weights to each of these on how important they are, right? Positive meaning that it is very important, negative meaning that it's kind of inverse. So it could be, less procedures is a lower hospital stay, right? And what you're trying to output is this, okay? And so mathematically, it's quite straightforward. It's just essentially a linear combination of different variables multiplied by a coefficient, okay? So again, I don't want you to go too much into the math, right? But this is what linear regression looks like. So you're trying to predict length of stay based on, for example, things like age, diagnosis, comorbidities. And what we're trying to optimize and find are what these coefficients are supposed to be, okay? Now, hopefully you've actually seen something like this, in, I think, maths methods or specialist maths, right? I think more maths methods though, which is, you're basically trying to find, based on these data points, a line of best fit, okay? And that line of best fit is basically this, but across multiple dimensions, right? If, for example, you just have two variables, like say with just one age and diagnosis, then it would look like this, okay? Okay, and so a single layer neural network is the exact same as linear regression, okay, with just a couple of bells and whistles, but broadly speaking, it's basically the same thing. We have a number of coefficients, which we now call weights, okay, multiplied by a set of features represented by this x1, x2, and x3. Okay, and because we need to account for the y-intercept, we add a bias term. Okay, so again, very simple, right? Supposed to be very kind of simple. And so we represented kind of in this structure here, which we call a neural network, okay, where these are different features. These are different weights or coefficients tied to the features. And then this is the output that we get. Any questions? So hopefully this is just merely kind of changing this function here into a graphical format. Okay, so we have the features here, the associated weights, and then this is the output. Okay, that is the length of stay. Okay, so now that we have a neural network, one thing that we need to measure is how accurate our line of best fit is. And to do so, we need to use something called a loss function. A loss function is a quantitative measure of how good your model is. And it indicates the accuracy of your parameters or weights. Okay, so that is your coefficients. So if, for example, your loss function is very high, so that is your loss value is very high, it means that this is not a very good line. Okay, so for example, the line might be like here or something, right? That's a very bad line, so your loss is going to be very high. If the loss is optimal, then your loss will be very low. Does that kind of make sense? So that's what we call a loss function. Now, a common starting point for this is a formula known, or a loss function known as the mean squared error, which I'll show you an example of. So say our model, which is our AI model, our neural network, has predicted this, okay? And this is the truth about how long the patient actually stayed in hospital. So how you calculate a mean squared error is you take the difference between these two numbers and then you square it, okay? Now there's a couple of reasons we do that. The first reason is we square it because if it is 1 day away, so say for example this is 5 days, the ground truth is 4, but instead this is 3, regardless of whether it was kind of above by 1 or below by 1, is the same amount of error. Okay, so we square it so that anything negative becomes positive anyway. And then it's quite a simple formula, we just take the difference between these two. So the mean squared error of this one would be 5 days minus 4 days squared, which is 1. For this one, it would be 12 days minus 10 days, which is 2. We square it, it becomes 4. And then this one is 7 minus 14, which is negative 7. We square it, it becomes 49. Okay? So the loss on this prediction is 1. The loss on this prediction is 4. And the loss on this prediction is 49. Now you can see how the further away we are, we actually punish the model a lot more. Right? The loss becomes quadratically higher as it guesses further and further away. Okay, so it's basically saying that, hey, you guess 5 days, the real answer is 4. That's a pretty good guess. We're not going to punish you that much, right? But if the real answer is 14 and you guess 7, that is a huge error and you need to fix it. Does that kind of make sense? Does anyone have any questions on this? This is kind of like the basics of neural networks. So if you're kind of not understanding anything now would be kind of a good time to fix it before we move on to more complex things. Any questions? Yeah, so yeah, if you want to punish a model even more, you can definitely use things like quadratic, you know, yeah, we'll talk about the dynamics of that later. But yeah, like people just start off with square because it's really easy to understand, right? And it's really, as you can imagine, you're trying to square a number. It's a lot easier in the computer rather than like trying to multiply it to the power 4, right? Yeah.
The method you're talking about now is mainly covering when you're dealing with like digit like number.
That's correct. Yes, absolutely. Yeah.
Are you going to cover how you might deal with things when you're dealing with like more word-based or?
Yeah, absolutely. We'll talk about that, but kind of as a basic, like neural networks are very good with numbers. So for example, if you're predicting things like, the chance of someone having pneumonia or, the chance, like how many days they stay in the hospital, all those are usually numerical outputs. You can also kind of, modify the numerical output into yes or no. So say, for example, it's like, you look at this chest x-ray, does it have pneumonia, right? So one way that we do that is basically say, if the score is above 50, right, then it's a yes. And if it's below 50, then it's a no, right? Where it's bounded by 0 and 100, right? So there's lots of ways to kind of modify numbers into words as well, right? So for example, things like binary outputs or, multiple outputs, it's possible to do. But this kind of structure is too basic for language, right? Because it deals primarily with numbers. Yeah, great question. Further questions? Okay, so let's move on. So a big question that people have is how do we minimize this error? Okay, and so we're going to talk about a very dummy case or a very simple case, which is that we only have one variable. Okay, so say that we only have a single variable to predict something else, right? So an example would be, I want you to predict the length of stay based entirely on someone's age. Okay, just entirely on someone's age. So there is obviously, as you might imagine, some correlation between that, right? Because, if someone's older, it's likely they will stay in the hospital for longer, right? If someone's very young, like say, teenage years or their 20s, they're probably going to stay in the hospital shorter than someone with the same condition, right? And then if they're super young, so that is, they're a baby or they're a neonate, they will probably stay there longer than someone who's like a child or an adult or a young adult, right? So there is some kind of correlation there. And so you can actually graph this out using kind of two axes, right? So this here is the mean squared error or the loss. And then this here is the coefficient attached to the age of someone. Okay? And so it could be, and so this obviously doesn't make sense with age, right? But say it could be that if our coefficient is very low, this is what the loss looks like. And as it gets kind of higher, this is what the loss starts to look like. And so you can see how you can basically map out this graph between the loss as well as the coefficient against age. So that is the weight. And when you take a look at this, you eventually see that there are actually maximums and minimums in the loss function itself. Okay, so when you map out the loss function. And so what we're basically trying to find is when the error is minimal. That is, we're looking for the global minimum, right? Because this is where the loss function is the least. And so therefore, this function has the least amount of error possible. Okay, kind of any questions from that? Yeah. Yes. So technically it won't be negative. You're absolutely right. So it should be that this graph could be, for example, here. But that's a really good catch. Yeah. Other questions? Okay. So when we assign a specific weight, we basically are saying that the loss function will start here. And we're trying to find this global minimum. And what we basically do is this thing called gradient descent. And so we won't go too much into the details, but you are trying to find a way to reach this global minimum. Okay? And so if we start here, it is actually possible to reach this. However, we do not know where this global minimum is ahead of time. And so, for example, if you start here instead, then it actually isn't ever possible for you to reach this global minimum. Because if you, for example, bring the weight, so kind of tune the weight down, it starts going here, you keep on tuning it down, it's going to look like you basically have more error, okay? And so the intuition that people use, right, and so I don't want you to kind of focus too much on the details, is that this is a little bit like a landscape. And so we call it the lost landscape, right? So say you start here, you basically want to walk downhill until you find this. But if you start here, then it's very hard because you need to go all across these hills. If, for example, you start here, you might actually start walking down here, okay? If you start here, then you might actually go uphill. So essentially what we're looking for is this global minimum, but you do not know where this is, and so you might start anywhere on this map, okay? And so if, for example, you have more than one weight, then it starts looking like this. Okay, so this is just merely two weights, so that is two factors that we're considering. If you have even more, then it starts to look like this, okay? And so part of the challenge is that as you increase the number of factors that you're considering, so say, for example, we have the length of stay, we might consider 10 different factors. We're basically in 10-dimensional space trying to find where the global minimum is. Does that kind of make sense? And so the framing that we have, and kind of the thing that you always keep in your mind, is just this basic thing here where we have a landscape and we're trying to find this global minimum, okay? And as we increase the number of factors, it gets increasingly complex. So it becomes what's known as the curse of dimensionality, which is you have so many dimensions that it becomes very difficult to find where the exact coefficients are, okay? Any questions about that? So again, this is more just about intuition, right? What we're basically trying to find is the global minimum in kind of a lost landscape. Okay, that's kind of the goal of AI, right? And these kind of axes here are the different weights for the different factors. Okay, yeah.
We have a question from the Zoom chat from Hee-Sang Han from Korea University.
Yeah.
So he says, I'm curious about how thinking before talking is carried out in LLMs. I thought the idea was to figure out the word with highest probability and put that behind the prior word. Does this have to do with using transformers?
Yes. So it's a great question, and we'll talk about it in a little bit later. But essentially, when we're dealing with reasoning models, right, which we'll cover tomorrow, the model actually talks to itself, right? So it does actually immediately start talking, right? And then it actually looks at what it's talking at, and that is considered reasoning, right? So it's very much like you having a self-dialogue with yourself, or you kind of talking to yourself before coming up with a specific answer, right? So it's very much, if you're doing an assignment, you might actually think about it first before kind of starting to jot down things or answer a question, right? So it still kind of follows a process where the model must talk first, but actually humans will not see what it's talking before it decides to have a final answer that a human can see. So it still follows the principles of just talking first. It will then hide this, and then a final answer is provided. Okay, so it's just kind of almost like user interface tricks to not show the user what it's thinking first, like its initial answer, and they will think about it, and then the final answer will be provided. That's a great question. Okay. Okay, so kind of moving on, how we basically frame AI is this lost landscape whereby we start at random areas on the map and we want to find this. And so there is an algorithm that actually ties everything together. And again, we don't need you to get into the math of this, whereby we basically have old weights and then we want to take a step in a certain direction in order to find this global minimum. And so how it works is a 4-step process. And again, we don't need you to kind of understand this that well, but we want to randomly initialize at a certain area in the lost landscape. We then want to calculate, using our neural network, our list of predictions, and then compare it to the ground truth. Okay, so this is called a forward pass. You want to make the predictions based on the weights. You then want to calculate the loss, which is this step here. So that is how much error there is. And then you do what's called a backward pass, which is we update our weights using gradient descent. Okay, so these kind of 4 steps are the basis of modern AI. And they essentially tie everything together, whereby you basically take a step in a certain loss landscape and then try and find that global minimum. Okay, so that's what we're essentially doing with AI. Now, backpropagation, so this kind of formula can be used regardless of the number of layers in our neural network. Okay, so even if we have just a single layer or hundreds of layers, this algorithm will work. And the kind of general form of it is this theorem called the universal approximation theorem, which says that a neural network with at least one hidden layer and a certain activation function can approximate anything, regardless of how complex that function may be. Okay, so even if, for example, we have this function here, a neural network, after many rounds of training, will eventually be able to recreate that function. Okay, and so kind of underpinning all this is that regardless of how complex something might be, so for example, a diagnosis decision, or how long a patient might stay at a hospital, or whether someone has a certain condition, a neural network will be able to replicate the statistical logic behind it, okay, if you do enough training. Okay, so this is a very kind of powerful theorem that underpins a lot of what we have right now in AI. Now, a lot of people talk about how deep neurons actually are, right? And so modern AI generally uses neural networks that are around this number of layers, so kind of like 10 to 50 layers, okay? If you do more, it can actually do more complex, complex functions, but then we run into other kind of compute issues and something called overfitting, which we want to avoid. So intuitively, you can actually break down different parts of the neural network. So earlier parts of the neural network we find usually deals with lower level features. So for example, things like edges, right? And kind of, circles, that kind of stuff. Mid-level features is you start to get objects like the heart or the lungs, right? And then higher level features is it's able to deal with the whole rib and chest system. And so you can actually break down these neural network features and see low, mid, and high level features when you take a look at what's actually happening in different layers. Under and overfitting. So there is this really important concept in AI. So you know how we were just talking about the line of best fit? It is actually possible to build a function so complex that it fits your data perfectly, but does really poorly when you provide it other data. Okay, so say for example, we want to build a function that divides this graph between X's and O's. Kind of intuitively, you might go like this, right? So if, for example, you've undertrained, so that is the AI is not well trained, it's just going to guess something quite random. If it is kind of just right, then it might guess what a human might guess. But if it guesses or is trained too much, then it might draw these kind of perfect lines that fit this data set very well, but doesn't really capture the greater trend, right? So it's kind of like a medical student who might learn about, this specific constellation of features representing a specific condition, but out in the real world, there's a lot of randomness and noise, right? So you might be completely wrong because you're basing it on assumptions, right? So that is a kind of classic example of overfitting or underfitting in models. And so this is kind of a very important problem that a lot of AI scientists will work on because it is very easy to actually overfit or underfit a model. And a recent kind of example where this happened was that OpenAI released a model that was very perfectly fit for the population, right? So that is, when you give the thumbs up or the thumbs down in ChatGPT, they actually, fine-tuned the model such that it was perfect for those who really like the model. And what they found was that this model was what we call sycophantic, which is it tells you exactly what you want to hear, right? So it's like, you might suggest like this really horrible idea and it's like, oh, it's a great idea, right? And that kind of led to some recent suicides, right? Because some people were talking about, having things like suicidal thoughts, and it would just say that's a great idea, right? Like this is how you can do so, right? Because it was overfit to the thumbs up that people actually gave in these circumstances, right? Because it was what people wanted to hear. So again, like this kind of problem manifests all the time. If it's underfit, it basically is saying that, an AI model is so general, it's not built for you, such that, it's not very well trained for you, right? It just kind of gives like general answers, right? So a lot of models aren't used because AI models aren't really tailored to what you need, what you want, right? And so, yeah, so this underfitting and overfitting still manifests today in a very, very big way because people can overtrain or undertrain models. Now, in terms of things like overfitting, there's lots of different ways to deal with it, and we won't really go into detail. But one of the most important things is more diverse data, right? So because they overtrained this AI on a specific subset of users, it basically led to very negative behavior for the AI. If, for example, they had trained it on a larger kind of proportion of users from, for example, different countries or kind of different things, right? It would be able to deal with kind of a broader cultural subset of different things, right? So, a lot of AI these days is trained primarily on Western audiences, right? So the kind of people that they get to train these models are usually kind of trained or educated in UK or US systems, right? And so there's a lot of Western kind of style answers to a lot of these systems. And you'll also see, for example, like the Chinese models have kind of the same issue, which is they've trained it primarily on Chinese data. And so therefore, there's a lot of ways that it answers is kind of Asian or Chinese in kind of its character, right? And so diverse data is actually one of the most important things kind of in modern day, which is being able to train AI models to deal with a wide set of circumstances that you do not expect, right? But as you can imagine, it's very expensive to do so, right? Because you've got to kind of get people from lots of different countries. Okay, so I've really barely touched on neural networks, but if you would like to learn more, there are a set of kind of YouTube lectures that we released for PhD students. So these are students who actually need to understand all the kind of ins and outs of neural networks, right? If you would like to essentially, learn a lot more about how to actually manipulate neural networks and use neural networks and play with neural networks, I would recommend these links. Neural networks are not really a kind of broadly used technology as much anymore. There's some researchers who still, very much like neural networks, but kind of modern AI has moved along, right? So I want you to kind of just get a feel for how neural networks work, which is that kind of gradient descent, kind of like this landscape of loss that we're trying to find the global minimum in, right? So it's just like a bunch of hills that we're walking in and want to find it. But beyond that, there's not much kind of, that kind of broad anymore that people use neural networks for modern research. Okay, so neural networks have spawned a whole bunch of advanced architectures that now kind of underpin a lot of AI. And so we'll talk a little bit about those. The first is the convolutional neural network. So if you're kind of interested in the visual recognition field, so that is diagnosing things on X-rays or CTs or that kind of thing, convolutional neural networks is what you'll need to learn about. And like I said, it was inspired initially by the retina, right? And so it's kind of a very cool architecture that has unlocked things like image recognition, diagnosing things on images. All of that is underpinned by this. And so if you do want to learn about it, there's some great courses about it online. Generative adversarial networks. This is another kind of cool network that was created in 2014, which basically pit together two different networks. One neural network is in charge of generating a fake image, and then another one is in charge of identifying whether it's fake or real. And eventually these two networks just keep on training each other, as you can imagine, because one network will get really good at generating fake images, and then another one gets really good at identifying between which one is fake and which one is real. And they keep on kind of just getting better and better and competing against each other. And so this was the kind of foundation of image generation, right? So this is the technology we had to use back then in order to create images, for example, of a cat, or a dog, or like a muffin or something, right? And this kind of underpinned a lot of that. It's since been superseded by something known as diffusion models, and we'll talk a little bit about that, I believe, tomorrow, or even later today, whereby you kind of have a noisy image, and then you actually denoise it to create a cat, right? And it's kind of very interesting, but they took a bunch of images, so like cats and dogs, that kind of stuff, added noise to it, and then trained an AI to do the reverse. Okay, and so modern kind of technology now, which is to generate, pictures of bananas or Will Smith eating spaghetti or whatever it is, right, is based on this thing called diffusion models. Now, RNNs and LSTMs is actually what we used to use for language. They're no longer used because transformers are a lot more powerful. But if you do see kind of papers here, generally it's kind of older language experiments. They were based primarily on how memory works, but since then have kind of been superseded by transformers, so we won't talk about it. But if you're interested in kind of old language neural architectures, you're going to see this word a lot, and it indicates that it's an older technology you're looking at. Reinforcement learning. So this was the technology that I mentioned was based on Pavlov's dogs, right? And so it's essentially rewarding a model when it does well and punishing a model when it does poorly, right? And so with this, we've basically been using it to train large language models to align with what our personal preferences are, right? So for example, if the model speaks out of turn or it answers poorly, right? Then we actually tell it, this is a we reward it if it does well and we punish it if it does poorly, right? So that's usually, if you've used kind of ChatGPT long enough, you might see two answers being written, right? And it asks you which one you prefer. On the back end, it's basically using reinforcement learning to teach the model that, hey, you're doing great or you're doing poorly, pick this one, right? And so you'll kind of see this as an important step in training large language models. All right, if you're kind of interested in any of these technologies, Stanford has a bunch of excellent courses that you can learn about. These do get a bit technical though, right? So you do need a bit of an engineering background to learn if you'd like to. But yeah, these are the kind of courses that teach you the basics of things like visual recognition systems, generative adversarial networks, natural language processing, so how to deal with language, as well as reinforcement learning.